Here at Mediumly, many of the systems we are interested in are known as complex systems. Complex systems are hard to define, and there is no exhaustive definition of what it means for a system to be complex. However, it isn't very satisfying for you if I say, trust me, you'll know them when you see them. So let's try and break down what I'm talking about. Here, complex does not necessarily mean difficult or hard, but rather refers to a system with multiple parts that interact. Out of these interactions emerge behaviour that is not characteristic of the individual parts of the system. For example, one neuron is probably not intelligent. In fact, it is not even the billions of neurons in a brain that make it conscious and intelligent, but rather the structure and connectedness of these parts that allow for complex behaviour to emerge. Complex behaviour like processing, perceiving, and reacting to the world around it. Some other examples of complex systems include a system of single cells that coalesce and emerge as a multicellular organism, like seaweed, or a jellyfish, or a monkey, or a human. Systems of molecules in the atmosphere that interact and form high-pressure systems, low-pressure systems, and ultimately cyclones, thunderstorms, and blue skies. Or even a meme going viral and spreading. As it becomes a part of our cultural consciousness, it will naturally evolve. Now, all these systems seem pretty disparate, but I hope over the course of the next few videos to demonstrate their commonalities. So to try and decipher what complex systems are, let's explore some of their common features. Number 1, iterative processes. Most of the time we are dealing with iterative processes. That is, simple rules being repeated over and over. Number 2, emergence through interaction and spontaneous self-organization of the system. The complex behavior of a system generally emerges from the interactions between agents and is not necessarily a feature of the simple rules that each agent follows. Complex systems display what is referred to as spontaneous self-organization, which basically means that the system organizes itself into distinct structures that are not encoded in the behavior of each individual agent. Number 3, evolution and adaptation. Agents will usually adapt and evolve as the system progresses through a series of feedback loops. Through the iteration of these feedback loops, the internal models of each agent change, which lead to an evolution of the system itself. To illustrate quickly these ideas and how they relate to the real world, consider a system of humans, each with an internal model of the things that they want and need. This system will spontaneously organize itself into some sort of economy that will initially follow some relatively simple rules. Number 1, human wants a thing. Number 2, human collects something to trade for that thing. The trade of resources allow each human to move towards their desired state. But as time goes on, each person's internal model will shift, as new wants and needs become realized. The way in which we talk about economies today, you might assume that they have a mind of their own. However, no human decided independently to create this economy. It merely emerged from the behaviour of the individual humans. It will also continue to evolve, perhaps becoming more efficient, but perhaps not. With an introductory understanding of what complex systems are, let's further explore each of these key principles. Number 1, iteration. We can look to nature for examples of these iterative complex systems. If we take the systems of particles that makes you, we can assume that every electron and proton will follow simple rules outlined by quantum electrodynamics and Maxwell's laws of electromagnetism. But to solve these equations is no easy task and would require repeatedly calculating every interaction that would occur, the trillions and trillions of collisions that would ultimately make you, you. This is an example of iteration, the iteration of the fundamental laws of physics, over and over until we've arrived at our desired state. But is following each particle the best way to view this system? This leads nicely into the second point on our list of features of a complex system. Number 2, emergence through interaction and spontaneous self-organization of the system. Once we have enough of these particles interacting and colliding, perhaps it is not useful and potentially very difficult to calculate every single interaction of every electron in our body. In fact, as these particles interact, they tend to form bigger and bigger molecules that seem to follow a new set of rules, namely the metabolic pathways that are crucial to life. This new set of rules has emerged from both the number of particles, but also the ways in which they interact, and and seem to have very little to do with quantum electrodynamics. These new molecules, following a new set of rules, will tend to organise into cells, which, in and of themselves, follow yet another set of emergent rules. These cells will organise into tissues and organs, and eventually into you. At each level, a new set of rules emerged, which dictate how the system will behave. And the system seems to organise without the full knowledge of the individual parts at each stage. At each level, it could be said that there is some form of intelligence, or, at the very least, the ability of the system as a whole to react to changes in the environment without the full knowledge of the individual parts. Number 3. Evolution and adaptation. Complex systems have the ability to respond and react to their environments. The agents of these systems will often form an internal model of their environment that will be updated as new information arises. Cells will follow the laws of physics, out of which emerge something like Darwin's theory of natural selection. Only those cells with an internal model that aligns with the environment will survive and reproduce. As generations of cells iterate through their life cycles, the systems they make up will evolve and adapt to better fit the environment. Another example illustrating emergence in complex systems are the pixels on your screen. Each pixel acts as an agent and has a given colour and brightness. But knowing the colour and brightness of every pixel tells you nothing about the picture you are looking at. It is only once you zoom out and examine the interactions of each pixel with its neighbours that a picture will emerge. A picture that contains so much more information than the colours and brightnesses of each pixel alone. Better yet, rather than each pixel just containing a single dot with colour and brightness, we could replace each pixel with its own picture. Again, modulating its brightness and reducing it to the size of a pixel, we can zoom out and see a picture emerge. So it really didn't matter how complicated our pixels were. We only really needed to model the important features. The rest became redundant. What is key is that you don't necessarily need a complicated model to understand a complex system. In all of these examples, it was not helpful to isolate the agents in each case, be they proteins or cells or organs or pixels. What is helpful is identifying which features are key in the interactions of these agents, those which will ultimately lead to complex behaviour. In fact, it seems to be a mantra of complex systems researchers that the whole is greater than the sum of its parts, meaning that it is probably more useful to understand how agents will interact rather than knowing every possible feature of the agents themselves. Complexity and emergence are crucial in gaining an understanding of the dynamical world of the medium. If we can distill some common features of these systems, we are better able to tackle any problem that might arise in our lives. Understanding complexity gives us a framework from which to design useful models to predict the future and understand the world around us. In this video, we explored iteration, emergence, and evolution, which seem to be pervasive in the world that we live in. These 3 ideas act as a great launch point from which to further explore the medium. In our next video, we hope to explore a simple model of a complex system and demonstrate these dynamics in action. If you want to know more about complexity, check out the books in the description below. And if you enjoyed this video, please subscribe.